Range of human hearing. Human hearing depends on both intensity and frequency of sound waves. Lower frequencies must have higher intensities relative to high frequency sound waves. So let's read the graph slide here that shows the variation of the intensity of sound as a function of a frequency. And this whole region, this whole purple region, represents all the sounds that are audible to the human ear. So, and this lower part of the region is the threshold of hearing, and the upper part is the threshold of pain. So what do I mean by threshold of hearing? For example, for a sound wave of frequency 50 Hz, the minimum intensity required for us to hear this sound, to be able to hear this sound, is 10 power minus 7 watt per meter squared. The minimum intensity for a frequency of 200 Hz is 10 power minus 10 watt per meter squared, and so on. Okay? However, as for the threshold of pain, for example, for 1000 Hz frequency, the maximum intensity must be 1 or 1 times 10 power 0, which is 1 watt per meter squared. Above this intensity, the ears are going to be damaged. So now deduce from the adjacent graph the range of audible frequencies for human ear. It goes from 20 Hz, the region goes from 20 Hz to 20,000 Hz. You can see that it's, like we say, typically or in an ideal case, greater or equal to 20 Hz and less than or equal to 20,000 Hz. But in reality, as an average of human ear, the audible frequencies ranges a little bit above 20 Hz and a little bit below 20,000 Hz. Now, referring to the adjacent graph, give numerical examples that justify the second statement of the given. So the second statement of the given is lower frequencies must have higher intensities. If we go check the threshold of hearing border here and compare, for example, points B and C. B has a frequency of 200 Hz and C 1000 Hz, so here the frequency is less. However, the intensity for lower frequency is 10 power minus 10 greater than the intensity for 1000 Hz. So for it to be audible, low frequencies must have high intensities. So we can take any 2 points and compare them on the threshold of hearing. We can compare A, D, B, C, AB, AC, BD, BC, and so on. So are there musical sounds of 1000 Hz and 1 times 10 power minus 6 watt per meter squared? So let's check this point. These are the coordinates of this point. 1000 Hz, we go vertically upward, and 10 power minus 6 here. So this is the intersection point. This is the point. It belongs to the speech region. However, the speech region is also a subset of the music region. So yes, this point or this sound belongs to the music region because the speech region is a subset of the music region. Now, does this graph describe an individual's hearing exactly? Actually not, because it only describes the average. So no, the graph is based on the average human ear. Each individual's hearing may vary based on the sound he is exposed to in his daily life. Maybe he's always exposed to high sound, maybe to low sound, maybe we have difference in the anatomy. Okay, so these factors do affect the range of frequencies audible by each one of us. But this graph actually represents the audible frequencies and intensities for average human ear. Now, are there musical sounds of 1000? We already answered this part. Now going to problem 3, sound in air. Sound wave is a longitudinal wave. As it propagates through a medium, it causes a change in the pressure of the medium's molecules. The threshold sound wave of frequency 1000 Hz propagating through air causes compressions and rarefactions at about 3/10 billionth of atmospheric pressure. This causes a maximum displacement of 10 power minus 11 meter of air molecule. And given that the average diameter of an air molecule is 10 power minus 10 meter, compare the diameter of an air molecule to the threshold displacement, then deduce why the ear is sensitive to the sound in air. Aside here, you can see different air molecules, oxygen, gas, water molecules or water vapor, nitrous oxide, carbon dioxide, ozone, methane, chlorofluorocarbon, and so on. So these molecules are all present in the air, of course in different percentages, but then we can find, and each one of them has a certain diameter, but we can take the average of all the air molecules, and it's found to be 10 power minus 10 meters. Now they're telling us here that a sound of frequency 1000 hertz causes 310 billionth of atmospheric pressure, which causes a displacement of 10 power minus 11 meter of air molecule. So we can see that the order of displacement and the order of dimension or the diameter of the air molecules are close to each other. So this 10 power minus 11 meter displacement is really detectable by the air molecule. However, if we take, for example, let's take another example just to make things clear and why do we have to compare the dimension of the order of displacement to the order of the dimension of the molecule. If you take an example, a large box of height 3 meters, and then a force is exerted on it or some pressure is done on it and causing it to move by 2 centimeters. Is really these 2 centimeters detectable for such a high box of 3 meters height? For sure not. So we do not consider this displacement, or it doesn't affect really the state of the box. However, in this case here, when a 10 power minus 10 meter molecule is displaced by 10 power minus 11 meter, so this is detectable by the air molecules. So we say that 10 power minus 10 is close to 10 power minus 11 meter. We conclude that the ear is sensitive to the sound in air since the displacement caused by the sound is close to the dimensions of the air molecules. Now this is a general knowledge. Sound wave has lower intensity in water than in air since water is denser than air. So though the same pressure is done, but this pressure is trying to come over denser molecules that are close to each other, trying to propagate through denser material. That's why it loses energy as it passes through this dense medium. And you know that intensity depends on the flow of energy. So the sound compared to the sound in air compared to the sound in water, the sound in air has greater energy or greater rate of flow of energy than that in the water. That's why the intensity of the sound in air is greater than that in water. Of course, here we're talking about while having the source at the same distance away from the receiver. So if you consider the source here and the receiver here, so the distance between them is the same. And in the water, the source here and the receiver at the same distance away from the source. So the intensity in the air by this receiver is greater than the receiver in the water, because as I said, as sound propagates through a denser material, it loses energy, and thus less energy means less power. Less power means less intensity of sound. And finally, here we have the pain threshold. The loudest sounds that the human ear can tolerate have an intensity of about 1 watt per meter squared. So this is known as the threshold of pain because sounds with greater intensities can produce pain in addition to hearing. So the highest curve in figure 2.2, as I explained before, represents the threshold of pain at each frequency. So I can ask you, what is the intensity? What's the maximum intensity of a sound of frequency 100 hertz? You have to refer to the threshold of pain border here. Or what is the maximum intensity of a frequency of 5000? So you have to do projection and refer to the axis here to know the answer. Now, exposure to sounds above the threshold of pain can cause immediate damage to the ear, even if no pain is felt. So even if you do not feel the pain at this instant, but it damages your ear. So prolonged exposure to sounds of lower intensities can also damage the ear. So whether you always really listen to very low sound or very high sound, this damages your ear. So note that the threshold of hearing and the threshold of pain merge at both high and low ends of the spectrum. This graph is really important to understand and to know how to analyze and how to read it, okay? Down here we have example of two objects that give sounds above that threshold of pain, which are the jet aircraft and the rocket. So that's why those who work with this stuff has to keep something in their ears to protect them from receiving high intensity sounds.